what you have to say. Let's have questions during the talk. And yeah, we are all looking forward to what you have to say. Thanks for coming.
Yeah, thanks, Jens, for the wonderful introduction. Hello, everyone. This is Honghao Fu. I'm going to talk about the effect of noise on MIP star. So when we talk about noise, we first think about the effect of noise on quantum circuits. But today we are going to consider a different model, the multi-prover interactive proof system with entanglement denoted by MIP star. Today we are going to see it also has, the noise also has a strong effect on this model, but in a very different way. So during this talk, please feel free to ask questions. I like interactions with the audience. And this talk is going to have 4 parts. In the first part, I will give the background of MIP star, both as a proof system and as a complexity class. In the second part, I will discuss the main results and its implications. In the third part, I will talk about our technical contributions, and I will end this talk with a summary of the result and some discussion about future directions. So before I introduce MIP star, let's consider the classical multi-prover interactive proof system. To motivate this, let's consider the following scenario. Suppose we get a very big graph. We want to determine if this graph is three-colorable. And this is too big for me to check all the vertices. So what should I do? A natural choice is to ask someone who is smarter than me for some help. However, this graph is big as an exponential large graph. Then even if they give me the entire coloring of the graph, I cannot go through the proof without losing track. So instead, I'm going to ask them questions to let them convince me that this graph is three-colorable. However, I don't want to be fooled by the smarter ones to believe the graph is three-colorable when it is actually not three-colorable. So this is the situation where we use MIP. So in the MIP proof system, we have a graph G. We want to decide if it's three-colorable. We send this graph to the 2 smarter ones called provers, Alice and Bob. And then we separate them very far away to make sure they cannot communicate. Then I start asking them questions. For Alice, I ask what is the coloring of a random edge UV. And then for Bob, I ask him what is the color of U or V on this edge. And then if this graph is three-colorable, then they can give me consistent answers. But if the graph is not colorable, then Alice can still fool me. But since Bob doesn't know which edge Alice got, it's very hard for him to give consistent coloring, and I will detect if they are lying. So this is the idea behind MIP. And indeed, we can define a complexity class MIP for all the languages L that has an MIP protocol. This MIP protocol must satisfy 2 conditions. The first one is called completeness, which says that if X is in the language L, there must exist provers with polybit questions and polybit answers that can make me accept with probability at least 2/3. This proof system must also be sound in the sense that if X is not in the language, all the provers, no prover can make me convince with probability larger than 1/3. And yeah, this is the completeness and soundness of the proof system. A very important classical result says that MIP poly-poly, so MIP protocol with 2 provers and then polybit questions, polybit answers equal next. Here, next is the exponential version of NP. And the three-colorability for exponentially large graph is a complete problem for this set. Okay, this is a classical MIP. And when we are in the quantum world, the provers can be quantum. And in this case, the first question is how do we define the quantum version of MIP? In the beginning, people came up with 2 different definitions, QMIP and MIP star. They both need to have the soundness and completeness guarantee. And they are similar in the sense that we are going to separate the provers so that they cannot communicate, but we give them the capability to share arbitrary quantum states. But they are different in the sense that the verifier in the QMIP protocol is quantum, so that he can process quantum state on polynomial many-qubit as a message. But in MIP star, the verifier is classical, so that he can only process classical messages.
So there's a bit, I mean, if there was a kind of a channel capacity, it would be like entanglement assisted classical capacity and quantum capacity in a way, right?
Yes, that's right. Yes, thanks. And if you just look at this definition, you may think, okay, QMIP must be powerful than MIP star because the verifier here is more powerful than classical verifier. But it turns out QMIP equal MIP star. This is proved by record Unger and Verseroni. Well, the key ingredient in that proof is a self-test of EPR pair using the CHSH game. So the idea is that they are going to mix the CHSH test with the instructions of a delegation protocol, so that each prover, he will get a question, but he will not know whether this question is from the CHSH test or from the delegation protocol. Then if he's going to be cheating, then the probability he got caught is very high. And so they can do this kind of, so this verifier can do this kind of a secure delegation of quantum computation to classical provers, to quantum provers through classical interaction. So next, let's look at.
Can I just ask a question?
Yes.
I might be missing something obvious, and I'm sorry if I missed it. In your example of using two provers to convince me that they have a coloring of a graph, why did I need them to be two provers? Why couldn't I have a single prover and I just ask any pair of vertices and check that they're the same?
Yes. Yeah, thanks for the question. So I didn't make this very clear. So the verifier in the proof system is a polynomial time machine, or polynomial time algorithm. If you only have one prover, I don't think there's a way for them to convince me that this graph, this exponentially large graph, is recolorable. For example, they can send me the coloring of the whole graph, but it's exponentially large. I cannot process it. And yeah, I should also mention, like in this setting, the verifier is polytime, but the prover has unlimited computational power. So they can do arbitrary computation to give me this proof. Yeah.
Okay, they could just be sending me back random colors and I wouldn't be able to tell that they actually don't have a coloring. I see.
Yeah. So I need
sorry,
to
again,
cross-check. Yeah.
Sorry, yeah, thanks for the answer. Another quick question, sorry. Can you remind me what the MIP star is, what the star is? I'm sorry if I missed it again.
Oh, yeah. Yeah, the star is for the entanglement. It's just to say the provers can share entanglement, but everything else are still classical.
Okay, thanks.
Yeah, thanks. Yeah, good question. Yeah, so
there's only one round, right? It's really like an entanglement assistance, right? I mean, there's initially an entangled resource, and then you can transmit all the classical messages, but there's no further quantum round, or you can always put it into the initial resource without loss of generality, correct?
Yeah. Yes.
Yeah.
Yes.
Good.
Yeah, in the definition, there can be many rounds of interactions, but like in the end, they prove just one round is enough. Yeah. Okay, so next, let me introduce the CHSH game. In the CHSH game, Alice and Bob are going to get questions from set 0, 1 with equal probability, and they need to send back single bit as answers. They can win this game if the sum of their answer bit equals the product of the question bit. And classically, with a classical strategy, they can win this game with probability at most 75%. But with a quantum strategy, they can win with 85%. And in the optimal quantum strategy, they need to share one EPR pair. And Alice's measurements are going to be the Z and X measurements. And Bob's measurements are going to be Alice's measurements rotated by an angle pi/8. Later, people realize that this is actually a self-test.
And this is also not only the optimal measurements in the CHSH game, but they are also actually the measurements to get like the tightest approximation to the CHSH inequality in the first place. Correct? Yes.
Yes, yes. Yeah, later people realize this optimal strategy is essentially unique. So what I mean is that if N is Bob using some arbitrary quantum strategy, but if they can win with probability 85%, then we can distill one EPR pair and the polymeriments from their strategy using local isometries.
Can I ask another question? Sorry, that's maybe a bit premature, and I also don't want to take away anything that you say later. So maybe you just want to skip. I mean, of course, that is true that the EPR pair is the only state that's consistent with these data, but it's much less obvious to say that you're close to an EPR pair if your measurement outcomes are close to those of the EPR of the CHSH game, right? So the robustness of that statement is a bit tricky, and that's why it's so difficult to get good bounds in self-testing. Are you going into this later, or is that not important?
No, I'm not going into the details of the self-test. I just want to introduce the idea of self-test.
Okay, good. Good to know.
Yeah. Yeah, so if you look at this CHSH game from the interactive proof point of view, you can view it as an interactive proof, not for some computational statement, but for the physical property that the provers share entanglement, and they can do polymeriments. And because of this self-testing guarantee of the CHSH game, the RUV paper makes it with a delegation protocol, and in some sense, it forced the prover to actually measure EPR pair even in the delegation protocol, and that's the idea behind that RUV proof. And since the RUV result, people have realized that we can just focus on the computational power of MIP star, and we can use self-tests as an essential tool in designing more powerful MIP star protocols. So in the first result is by Ito and Vidic. They show that NEXP is containing MIP star. So NEXP equals MIP. So this result means that MIP star is at least as powerful as the classical MIP. But in this result, they just prove some protocol is quantum sound. They didn't use self-test. And then after this result, people start to build more robust and more efficient self-tests of EPR pairs. More efficient means I want to send you fewer bits to make you convince me that you have n EPR pairs. And more robust means I can tolerate more corrupted qubits in your EPR pairs. And the latest one, or like in 2019, Natarajan and Wright use efficient self-test for n EPR pair, which only use log n bit of communication and can tolerate like 1/log fraction of corruption. They use that to prove that NEEXP is containing MIP star. So NEEXP is the exponential version of NEXP. So this means MIP star is strictly more powerful than MIP. And the key idea is to use self-test to get question reduction and answer reduction. Namely, they can transform an MIP star protocol with poly n-bit communication to log n-bit communication while maintaining the completeness and soundness guarantees. And then, yes.
Sorry to interrupt. So I understand why this Natarajan and Wright result of 2019 is important from the other one, but by proving that an NEXP is containing MIP star was already triggered, because I mean, it was not triggered. If it's not, can you explain why MIP is strictly less powerful than MIP star?
So sorry, sorry, can you repeat the question?
Yeah, sorry, I was confusing myself. So, I don't know, in mind, and of course I'm not expert in these things at all, but it's kind of trivial that MIP is contained MIP star. If I'm not wrong, I'd like to know at least an intuition why it's not already included in MIP star. Is it clear the question or not?
Sorry, I still couldn't
sound-
hear
It
well.
sounds
Lorenzo,
a
your
bit-
audio is
Yeah,
pretty
the
Yeah,
audio is
the-
a little bit wobbly. I don't
your
know.
question is probably clear, but we can't hear you well.
Oh, sorry. I don't know actually. So, and can you hear me now?
It's okay, but it's not super good. It's not super easy. Are you in the office or?
Okay. No, okay. I have chat and we can discuss later.
Okay.
Maybe you can type it in the chat and
Yeah, I think the question was, it's already known that you showed this result before about how MIP connects to Next. And I think Lorenzo was wondering, is the connection between MIP and MIP star clear?
Oh yeah, so the soundness of classical MIP only holds against classical provers. When you have quantum provers, the soundness doesn't like carries naturally to the quantum setting. You need to reprove the you need to redesign the protocol to make sure it is quantumly sound. You cannot just reuse the classical protocol. That's not going to be quantum sound. And so that's why why this first result is non-trivial. It's not just like you can ignore the entanglement. It's not as simple as that. Yeah, okay, thanks. And then, yeah, after 1 year in 2020, Ji, Natarajan, Vidi, Red, and Yuan, they prove MIP star equal RE. So here RE is a set of all the languages that can be decided in finite time. And the halting problem is a complete problem for this set. What they show, like what's the important technique contribution is that they make the question reduction and answer reduction recursively composable. Here to prove this result, the first version of QR and AR, they can only be applied once. And then in this version, they improve on it to make sure you can apply it multiple times and it still works. So this result basically tells us if there is a MIP star protocol for the halting problem with polybit questions and polybit answers, such that if the Turing machine halts, the prover can convince me with certainty using many EPR pairs. And if the Turing machine doesn't halt, no provers sharing any state can convince me with probability bigger than half. So this is the result so far about MIP star. And then from the completeness statement of all this result, you can see they use many EPR pairs. And then this makes us wondering what will happen if the EPR pairs are noisy. Namely, what if, and we consider the first simple case, what if the EPR pair is subject to some depolarizing noise? And here epsilon is an arbitrary small constant. And later we are going to use a new notation for MIP star. Here, the first two quantities are still the question length and answer length, but the third quantity is the state that the prover is going to use. When we specify the state, it means the prover can only use this state, but they can have many of this state. So the previous MIP star equal RE result basically says if the prover only have EPR pairs, this complexity class still equals RE. And my co-authors Minglong and Peng Hui, they are the first to consider the effect of noise on MIP star. In 2021, they show that if the EPR pair is subject to depolarizing noise, then this complexity class is contained in R, which is a strict subset of RE, which is a set of all the computable languages. They basically use some Fourier analysis techniques, and we are going to use some of their techniques too today. And they also prove that even for QMIP, when you have depolarized EPR pair, it's also contained in the computable class.
Can I ask you a question? When you use like Fourier techniques, I mean, that smells as if the specific form of the noise played an important role, that you have to be depolarized in a way, right? And I'm also saying this in the light of the insights we had recently on non-unital noise, so that like in some ways, non-unital noise can be quite different from unital noise. Say in variational circuits, you have no baryon plateaus and so on, and there's in a specific sense to become classically efficient and simulatable. So here, to come back to your setting and my question, due to the square picture, you have to have a depolarized state, right? And that's set in stone. Is that correct?
Yes. Yes,
Okay.
absolutely. Yeah.
Very good.
Indeed, yeah. This set of technique is specifically designed for this depolarizing noise.
Okay, that's what I guessed. Okay, very good. Thank you.
Yeah. Okay, these are all the background about MIP star. Next, I'm going to move on to our results. So we first prove an upper bound on the number of useful depolarized EP ampere. So we can specify an MIP star protocol by this tuple, and the first two sets, X and Y, are the question set, AB are the answer set, and the mu is question distribution on these two sets, and the V is a predicate that takes X, Y, AB and determine whether the verifier should accept or reject. And we define n-copy strategy to be a quantum strategy that uses n of the depolarized EP ampere. And we define omega n to be omega n for protocol pi and the share state psi epsilon to be the maximum winning probability you can get over all the possible n-copy strategies. So yes.
Do you require that the verification can be done efficient here, or like that the verification function?
So the omega n, do you mean if it's easy to compute?
Verification.
Verification should be like polytime, right? Yeah, this V should be like polynomial time classical algorithm. So our theorem 1 says that given parameter epsilon delta, m-dimensional depolarized maximum entangled state phi epsilon, and this protocol pi, there exists a quantity capital D, which is computable from all these parameters, such that for all n bigger than D, the maximum winning strategy on n-copy strategies cannot exceed the maximum winning probability on d-copy strategy by more than delta. And then this D depends polynomially on the size of the question sets, exponentially on the size of the answer sets, and 1 over delta, 1 over 1 minus epsilon, and log n. So importantly, this D is independent of the n here. And here I should say like the epsilon is noise strength, delta is the approximation imprecision, and the m is the dimension. So you can take all these quantities to be constant. So you can say it only depends polynomial on the size of question, exponential on the size of the answer sets. So it means that under this depolarized noise, even if you have more copies of the noisy state, it doesn't give you much benefit. It doesn't increase your accept probability in this protocol by much. This is a message we want to give in the
There will be some growth, but this will be like tiny, like log in the number.
Sorry?
So it will grow a little bit, but only logarithmically with m.
Okay, yeah. Yeah, this is theorem 1. So with theorem 1 and a positivity tester, we can give a next algorithm for MIP star with noisy EP ampere. So this NX algorithm is going to determine whether the accept probability of this MIP star protocol is above or below a certain threshold. And by next algorithm, I mean, it's like just like an NP algorithm. It has a prover and a verifier, and the prover need to send the certificate to the verifier, and the verifier need to check this certificate. The difficulty here is that we are going to deal with exponentially large matrices, so that we need this positivity tester to determine whether you give me a valid strategy, whether the matrices in this strategy are actually positive semi-definite. And then we also prove that we can modify MIP protocol for next to make sure this new protocol is summed against provers sharing the noisy EPR pairs. And then we can show next is contained in noisy MIP star. And
Sorry,
then,
I think I missed that. Sorry, I was slow. This positivity tester, this is like a property testing protocol for positivity, or what is this exactly?
yeah, it's like it's still an NX algorithm. So you have there's a matrix. I give you a certificate that this matrix is positive, and then the verifier check whether it is indeed positive. Yeah.
Good, thank you.
I'm going to talk more about this like later. Yeah, so if we combine in these two results, we prove that noisy MIP star equals next. And to concretely justify, so first recall, if you have EPR pair here, then this should be RE. And now to concretely justify this, it is a noise that destroys the computational power. We actually design a new answer reduction technique based on the first answer reduction given by Natarajan and Wright. We use this to prove that if instead of the noisy EPR pair, you give them actual EPR pairs, you recover the full computational power of RE. So these are the three main results of our paper. Next, let me discuss the implications. Let's make a comparison with the effect of noise on quantum circuits. When we talk about noisy quantum circuits, we mean each gate in the circuit is subject to some noise. And then the noise should accumulate over the depth of the circuit. In this case, in the wonderful new paper by Jens and the students here, you guys have shown that it effectively reduces the depth of the circuit to logarithmic. So as the noise accumulates, you get a depth effect on the circuit. But in
that's of course precisely what I mentioned, what I meant earlier. Yes.
Yeah, also I need to mention this figure is taken from the paper, and maybe
yes, of course I've noticed this, but okay, yeah, that's what I meant. Okay.
Yeah, it's a very, I couldn't make a better figure, so I just use this one. But in the non-communication model, only the EPR pair is subject to noise. And the measurements, they can be arbitrary depths, and they are all accurate. So you don't have noise in the measurements. So effectively, after you apply this depolarizing noise, only the yellow qubits are still working, and the noise effectively kills all the red qubits. So that even if you add these qubits, you won't increase your winning probability by much. So in this sense, we have a Wiz effect when we apply the depolarizing noise. And it doesn't have any depth effect. In fact, Alice and Bob's measurement can have arbitrary depth. There's no effect on that. And then if we look at the theorem 2 and theorem 3, we notice that it means in the no communication model, we cannot do error correction. We cannot correct the depolarizing noise and distill the EPR pair from the depolarized, from the noisy EPR pair. Because otherwise, if we can do this, then we can recover the full computational power of MIP star. However, we also notice that if you have partially entangled states, we can still distill the EPR pair with only local operations and no communication. And this is called entanglement concentration in literature, and I think it has been studied like very early. But from all these 2 points, you can see this noise are all unital noise. So we don't know what's the effect of non-unital noise on MIP star. The second result is
no, I'm not sure I'm following. Sorry.
yeah.
What do you mean that EPR cannot be distilled from the noisy version? Why not?
It means like if you cannot communicate, if Alice and Bob cannot communicate.
If they cannot communicate, then okay, I see.
Yeah.
See. Okay, no, then that's clear, of course. Oh no, I get it. So in the no communication model, okay, yes. Also, I was about to say something, but I discarded immediately, which is you might know this quantum refrigerator proposal by Daniel Gottesman, which is beautiful. It's one of the early papers that looked at the impact of non-unital noise and says lots of interesting things. And one of the points made is that non-unitality or amplitude damping can be a resource in that if you can cool down systems, you get clean qubits that you can use in error correction like schemes. So that sometimes this can be even better than having no noise because you have a resource of clean qubits.
I see.
Yeah, but that's not in contradiction to your statement on no error correction, because literally you would have no communication between parts and that would be ruled out. Okay, so I'm happy. I understand what you say.
Yeah, thanks. Yeah. Yeah, actually, I'm not very familiar with the quantum refrigerator. Maybe I will look into that. Thanks for
Well, it's a bit of a niche paper, but it's quite beautiful.
Okay, yeah, thanks. Also, the second implication I want to say is that our result means the depolarizing EPR pair is not useful at all for MIP star. This is because noisy MIP star equal next equal MIP. So even if you share depolarized EPR pair, it doesn't give you any advantage over classical where you don't have any entanglement. And the third implication is that we actually need maximum entangled state to achieve the full computational power of MIP star, not just entanglement. Before this result, people think MIP star is powerful because the prover can share unlimited entanglement. But under any entanglement measure, if you have unlimited noisy EPR pairs, you still have unlimited entanglement, just like if you have unlimited EPR pairs. However, as it turns out, noisy EPR pair is not useful at all, which means our result cannot be explained by any entanglement measure theory. So this
And that also, I mean, sorry to say something very stupid, but well, I feel free to do so nevertheless. So this is true independent of epsilon, right? And that's kind of the surprise value. Like even a small epsilon will kind of kill the show. You need a exactly maximally entangled state.
Yes. So epsilon can be arbitrary small constant. Yeah.
Which is kind of funny.
Is it like literally epsilon has to be literally 0, or would it suffice to be doubly exponentially small?
No, I think literally 0, no?
Or something.
If epsilon is 0, you have an EPR pair, right?
Okay, but what if it is like 1 over busy beaver function of n? Would this still be sufficiently small, or would this already be like any arbitrarily small?
So yeah, so if you look at this result, it's like a 1 over 1 minus epsilon. So like 1 minus epsilon is like inverse poly, then this upper bound is going to be blow up and you get like a larger class. It means like if you have very, very small noise, then it is still a little bit useful. But if it's a small constant, if the noise is small constant, this is not useful at all.
Okay.
Yeah. Thanks.
Astounding. Yeah, but maybe you will give some more intuition on this later. When I can guess where this is coming from, but still very interesting. Thank you.
Yeah. Okay, next I'm going to talk about the techniques we used in this paper. The first is about Fourier analysis. We generalized some results for the analysis of Boolean functions to matrix analysis. So let me first give some background on like the Pauli spectrum of Hermitian matrix. If we look at the space of all the Hermitian matrix, it is a linear space. We look at the Hermitian matrix acting on n qubits, and it's a linear space. And we can define the inner product on this space using the normalized trace. And then with this trace, we can define an orthonormal basis for this space, which is basically the tensor product of the polys. And then we can expand a matrix in this basis. And the coefficients, or we call them the Fourier coefficients, they are denoted by p hat sigma, and this sigma tells you which basis this is. So you can calculate this coefficient by taking the inner product of the poly basis and the matrix P. Then we define the degree of a matrix P to be the maximum weight of the sigma such that P hat sigma is not 0. So sigma is from the set 0, 1, 2, 3. Then the weight of sigma is the number of non-zero entries in the sigma. We then using, like, if you take the inner product of P with itself And using the orthogonality of the poly basis, you can prove the Parseval theorem, which says that if you take sum over all the sigma of P hat sigma squared, you should get the normalized 2 norm of P squared.
This I understand, but just to be sure on the previous step, I mean, sigma is a string, right? With entries from 0 to 1, 0, 1 to 3, labeling the Paulis, and the 0 would be the identity. So this length is in this 0, 1 to 3 valued string, the number of non-zero entries, aka the non-identity Paulis. Is this correct?
Yes.
Very good.
Yeah. Yes. Yeah, 0 is identity, so we count all the...
Yeah, okay, I got it.
Yeah. Okay, the Parseval theorem. And then we define the influence of radius I to be the 2 norm square of the difference between P and the new matrix obtained from P by replacing its action on the S register by identity. So it measures, so let's think about this way. If P doesn't touch the S register, the influence is 0. If P only acts non-trivially on this register, the influence will be 1. And then indeed, we can prove that this influence of the S register equals the summation over all the sigma such that sigma I is not 0, meaning sigma I is a non-trivial poly, and we sum all the Fourier coefficients square. So this influence tells us how much weight in the poly spectrum is on the non-trivial action on register I. And this is a quantity we generalize from classical Boolean analysis. And then based on this...
So this step is not entirely trivial, you say, right? I mean, it's a 2 norm, so it's just the sum of elements squared, but you say it's not obvious why the second line is the same as the first one.
Oh, that's right, yeah.
Okay.
Yeah, you need some steps to prove that. But this line should be easy. So if you take the sum over all the individual influence, you should get the total influence of the matrix P. And this quantity is upper bounded by the degree of P times the 2 norm square of P. Basically, if you use the previous equation, you can see each P hat sigma is double counted. And the number of times it is double counted equals the weight of sigma. And the weight of sigma is upper bounded by the degree, so you have like this upper bound degree times 2 norm square. This is like the background part of the Fourier analysis. And then I'm going into the proof of theorem 1. So in this proof, we are going to be given an n-copy strategy. And we are going to modify each of the POVM MXA to get a d-copy strategy that only acts on d-copy of the noisy EPR parent that uses new POVM MXA tilde and NYB tilde. This modification takes several steps, but like for each POVM, it's the same procedure. And in each step, we want to make sure the accept probability doesn't change much. And then we want to also make sure that after each step, the POVM, the matrices we get are still close to the set of positive matrices. So let me get started. In the first step, we are going to smooth the POVMs. We are going to apply tensor products of depolarizing channel on each qubit. And then if you look at the matrix P in the poly basis, the effect is expressed in this equation where we apply this delta rho to each of the poly. And this rho here will be a small constant that we pick. Then the depolarizing channel doesn't touch the identity matrix, but add a weight rho to all the non-trivial poly. This equation equals rho to the power of the weight of sigma times the original term. This means for all the high degree terms, their coefficient will be very small. In this sense, the poly spectrum is smooth. And then we can just drop all the high degree terms. So we define P1 to be the summation over all the low degree terms of delta p. And then because this row is very small and we only chop off all the high degree terms, this doesn't change the matrix by much. It doesn't change the accepted probability by much. And at the same time, the P1 are still positive semi-definite.
I see, but here the previous setting is used, right? In that you can really brutally chop off the full tail and it doesn't hurt you so much.
Mm-hmm.
Okay.
Yeah.
Thank you.
Yeah. And here we pick D to be a constant. Here, constant, I mean, it is independent of n, but it may depend on some other quantities like epsilon and delta. Okay, now we have the P1 is still a big matrix. It's a 2 to the n by 2 to the n, but it's low degree. And then if you recall, the total influence is the degree times the 2 norm. It means the total influence of P1 must be smaller than some constant D, which means that the number of registers with influence bigger than some constant tau must also be a constant, which is we denote by h, and it is D divided by tau. And without loss of generality, we can say the register 1 to h are the high influence registers. And in the next step, we are going to deal with low influence registers. In this step, we are going to apply the invariance principle. The invariance principle tells us we can replace the low influence register by random variables. So if you keep the polys acting on the high influence registers as they are, but replace all the rest of the polys by random variables, you get this matrix P2. The idea is
that's interesting, but I mean, I'm sure you will be using some sort of large deviation bound or something. But is there an assumption on the probability measure you can allow for, so that you're saying that typically the matrices you get are sufficiently close to the chopped off version? But what's the assumption on the random variables that you need to make this work?
Yeah, I cannot recall the exact condition, but like Gaussian variables or like +1, -1 with equal probability, those kind of random common random variables works here, and we pick Gaussians here. Yeah.
Very good.
Yeah, and then when you make the changes, you can change the polys one at a time, and each time you change, you incur an error of like the influence of the register. So these are all low influence registers. So this error is going to be bounded. And this is a generalization from the invariance principle on the Boolean functions. And for the Boolean functions, the invariance principle is a generalization of the central limit theorem. If you look at the central limit theorem, it says x1 plus all the way to xn divided by square root n. That's like a Gaussian. And then that works because the influence of each xi is only 1 over n, which is small. So you can do the replacement. Here, yeah, like I mentioned, all the gi are going to be a Gaussian. But if it's g0, if sigma I is 0, then it's just a 1. There's no randomness. It guarantees is that if you look at the distance from P1 to all the PSD matrices, it's going to be very close to the expected distance where you take the expected value over all the random variables. And then after this replacement, we get 2 to the h by 2 to the h random matrix, where h is independent of n. But we have n minus h random variables that determines this random matrix. Here, the size of the matrix is small, but it's random. And in the end, we want to get deterministic strategies. So we cannot just stop here. There are more steps we need to take. So in step 4, we are going to reduce the number of Gaussian variables. This is some technique we use, we kind of borrow from the classical literature. We show that there exists a matrix M such that if we can replace Ji by the inner product of Mi and this random vector x tilde, where each entry of x tilde is going to be a independent random Gaussian, but the length of x tilde is n0, which is also independent of n here. So we can have P3 to be just as before, but for each Ji, they are going to be replaced by this kind of inner product of the matrix and the random vector. So at this point, the random matrix is as small as in the previous step, but the number of random variables is n0. And then it's roughly the time we can change this random matrix back into like a fixed matrix. So in the next step, we are going to apply the inverse of the invariance principle. But actually, before this step, there are some steps to make sure the random matrix, each entry in the random matrix are of some like a very nice form. But I'm not going into the details here. The idea is that if we let big D to be H plus N0, we can replace all those MXI terms back into polys. And then we get this P4, which is only acting on D, capital D qubits. So this P4 is going to be is close to the final form we are going to get. The final step is to make sure each P4 is a PSD matrix. So we are going to just keep all the positive eigenvalues of P4 and then put all the elements of a measurement together and renormalize them together to get back to POVM. Then we are done in this co-modification procedure. And
but rounding, I mean, it's a bit more than that, right? Because you need, I mean, you get positivity for free, but you have to have the identity. So it's, I mean, that would be like, I don't know, like an semi-definite problem or something to make sure that the terms are positive semi-definite and that sum up to 1. Is it a bit like that, or what is the rounding?
Yes, exactly. So when I say renormalization, I mean to renormalize them to make sure they sum to identity.
I see.
Yeah,
okay.
Basically, if you just keep the positive eigenvalues, you don't have that guarantee. You need to.
I see. Then it's actually quite similar to what I've said. Mm-hmm.
Yeah, that's right. Yes.
Good.
Yeah. So in the end, you can see the D. We prove that D is only of this form. It's independent of it. So this concludes the proof of theorem 1 here. And then to prove that we have an NX algorithm for MIP star, we okay. So the idea here is that the prover is going to give a certificate that a protocol, that there is a strategy that wins this protocol with certain probability. But the certificate, the first idea is to send all the Fourier coefficients of all the POVMs in this strategy. But when the length of the question is poly, the size of the question set is 2 to that number, so it is exponential in n. So the total number of all the Fourier coefficients is going to be doubly exponential. So the verifier won't have enough time to process all the Fourier coefficients. So instead, the prover is just going to be like in the first step. They are going to smooth the POVMs and then send only the low degree smooth coefficient back to the verifier. And because the degree is a constant, they are only exponentially many of them. So it's a valid certificate. After getting this certificate, the verifier needs to check 3 things. The first thing is whether the elements in a measurement sums up to identity. The second thing is that if the accepted probability of this strategy is close to the target, it's not 1, it's the target probability in this problem. And the third thing is to check whether each matrix is a positive semi-definite matrix. The first and second thing are easy to check. They are direct calculation on the Fourier coefficients. But third one is not so trivial. Because the matrix is acting on exponentially many qubits, this matrix is doubly exponentially large. So you cannot just like diagonalize the matrix. So instead, we come up with a positivity tester for this task. It's also an NX algorithm, so the certificate is basically all the low degree Fourier coefficients. And the idea for the positivity tester is, again, using the invariance principle. The verifier can calculate all the high influence radiuses. then they can replace all the low influence radius by random variables. And recall this guarantee on the distance to the PSD matrices. So the verifier only need to evaluate this expected value. However, there are like D or exponentially many random variables. So he cannot evaluate this directly. So instead of using true random variables, they use pseudo-random bits. And then to evaluate this expected value, it is suffice to evaluate all the C's of the pseudo-random bits. And that is something they can do in exponential time. And this concludes the positivity tester and the NX algorithm for MIP star. Noisy MIP star. So any questions about this part?
Well, I think I get the idea. It's very nice. It's incredibly beautiful.
Thank you. Thank you. Okay.
There's the question in the chat.
Question?
How important is kind of the depolarizing noise here at your tool? Like,
Oh, yeah.
Well, like, I mean, do you believe, I guess, that it's, it's due to the proof technique, or that it's basically a true factor that you need depolarizing, or I mean, like unital noise with a single 6 point?
We need this to be a unital noise so that on each subsystem, the state looks like identity. And we want something we call the maximum correlation of this matrix to be less than 1. So depolarizing noise will satisfy that condition. And basically in each step, when we try to bound how much change is in the accepted probability, we are going to use the partial state to be identity that condition to make sure this calculation is only about the Fourier coefficients. Yeah, so it's like everywhere in this proof.
Like, do you expect it to be a necessary, like a necessary condition, or just that the proof just meets it? Like, is it like just like, would it also collapse under amplitude damping noise, or would it be like, just what do you believe, or how does it? Like,
okay, my impression is that we are going to have some new Fourier analysis techniques. Like, for example, we need to come up with some new techniques to prove the invariance principle in the case of non-unital noise. Yeah.
And so this replacement of randomness by pseudo-randomness is just for computational effort reasons, right?
Right.
Mm-hmm. Yeah.
Right. And yeah, this is also a classical technique. There's nothing quantum here.
Yes. I understand. I mean, this is like off the shelf, so to say, from classical information theory. Yes.
Yes.
What about other unital noise that is not depolarizing, like for example dephasing or bit flip? Right, it would only destroy the dephasing would only destroy the X and the Y operator, but not the Z operator. So do you have? I mean, is it important for you that this works for every P?
Probably the Fourier method, right, is probably tailored to this, I would imagine.
Yeah, but then you really need local depolarizing noise, because amplitude damping will leave the 0 intact, and anything that's non-depolarizing will leave something intact.
Yes. Yeah, we didn't discuss this very much in the paper. Yeah, I'm not sure about the bit flip, actually.
Right, so if X appears in your Pauli operator here, the bit flip will leave it intact because it commutes with X.
Right.
So you don't get this damping in the row to the size of D or.
Okay.
But what I don't understand is if if that's a problem, right? Because I don't know if this is supposed to hold for all P's or how that enters. At this row to the, exactly here, the row to the size of sigma. There you need that your noise is damping your Paulis, right? But if your Yeah.
Yeah, I mean, this is like some new noise we add to the operator. This is not like the effect of the original noise on the EPR pairs.
Oh,
I think, okay, this is my guess. So if you have like those bit flip errors, I think this step still works, but I'm not sure about like the those like the influence sorry, the inverse principle, those kind of steps where they will work. That's a question. Yeah, I'm not sure. Yeah, but thanks for the question. Yeah.
Could I ask about the intuition behind all this? Why like, because naively I would expect that maybe you can like distill your EPR your perfect EPR pairs from the noisy. So why is that not possible? Or
because there's no classical communication, right? Is that the point?
Yes. Yes.
Ah, right. Cool. Nice. Yeah. Thanks.
Yeah, it's important they cannot communicate.
Yeah, because otherwise, I mean, Jonas would be just right. That, yeah, interesting point. Cool.
Yeah. Okay, next, let me talk about the answer reduction part. So in a general MIP sub protocol, let's recall like the verifier want to determine if some instance we call input is in the language or not. It's going to ask questions, polylength questions, and then receive polylength answers. But if for some reason the verifier doesn't want to read the long answers, it's going to apply the answer reduction. So the goal of answer reduction is to make sure the verifier can only read fewer bits from the prover, but at the same time, the verifier can still check its verification predicate, or in other sense, to make sure to maintain the completeness and soundness guarantee of the original verifier. So the high-level idea is that the prover, instead of sending back the long answers A and B, they are going to compute a proof that they have a and B that satisfy the verifier's predicate. And then the verifier only need to ask XY and some queries to the AB and the proof pi. And then the prover only need to respond to the queries instead of sending back A and B. So this reduces the length of the answer. So here the key components are PCP of proximity and locally testable codes. Here PCP stands for probabilistically checkable proofs. And the difference between PCP and PCPP is that in a PCP verifier, he knows the entire input and he will probabilistically check the proof to accept or reject the instance. But in a PCPP, the verifier doesn't get to see the whole input. He can only query the input. Then that means if the input is a no instance, but it's very close to the yes instance, there's no guarantee that the verifier is going to reject it. But if it's very far from the, but if the no instance is very far from all the yes instance, then the verifier can reject it. So we have the proximity in its name. And locally testable codes are like classical error correcting codes where you can just query a few bits to determine if it's a valid encoding or not.
Yes, but these are all beautiful and extremely powerful techniques, and it's absolutely super nice. But they're all classical, right? This entire slide is classical.
Yes. The only quantum part of this
okay, good.
we are going to make some quantum sound. Yeah.
Yes. Oh, yeah. I anticipated this. Okay. Sorry.
Yeah. No. Good question. Yeah. So yeah, we want to make them quantum sound, and then so the theorem we prove is that if we start with MIP star protocol poly, and it satisfies the condition, if the input is in the language, then the prover has a real commuting symmetric strategy with value 1. Just think about that. They have an EPR strategy for this. And then we prove that the answer reduced verifier is in MIP star poly 1, such that if the input is in L, there's a value 1 strategy. And if it's if it's not in L, we have a constant soundness guarantee. So this F, function F is independent of everything else. It only depends on epsilon. And then we generalize, so Natarajana and Wright, they give the first answer reduction. They reduce poly to log, and they use the Lodiri code as the error correcting code. We improve on that to use the Heidenmark code instead. So Heidenmark code is a code where you encode an n-base string by taking the inner product of this string with all the n-base strings. So the code word is of length 2 to the n. But the next property of the Heidenmark code is that if you query the code bit at location x, y, and x plus y, you should get 3 bits that sum up to 0. This is called the linearity test of the Heidenmark code, and this is also like a locally. So this Heidenmark code is also a locally testable code. So next, let me introduce the PCPP. It's for a pair language on 2 strings, and we define LX to be all the Y such that the pair XY is in L. And in a PCPP, the verifier gets the explicit input X and the length of Y. And then he's going to query Y and the proof pi here. So the input X is the explicit input, and Y is the implicit input, where he can only query. And then the PCPP is going to be determined by this 2 parameter S and gamma. The completeness says that if XY is in L, then there exists a proof such that over all the randomness, when the verifier can query Y and pi, he's always going to accept. And the soundness says that if Y is gamma far from LX, then for every proof pi, the probability that the verifier accept is no bigger than S. So that S is the soundness parameter and the gamma is the distance parameter. In the language of MIP star, or in the setting of MIP star, we need this PCPP to work on a pair language where the explicit input is the instance, we call it input, and then the question X and Y. The implicit input is the answers A and B. These are the this A and B are the answers prepared by the prover, but not sending back to the verifier. So you notice here the verifier, PCPP verifier can only reject the instances that are far from the yes instances. So we want to improve that to make sure it rejects all the non-accepting A and B. So how do we deal with this? Very simple. We just use an error correcting code with distance bigger than 2 gamma and let the provers encode the answers A and B. So we define this language L-inc to be the tuple input XY, encode A, encode B, such that input XY, AB are accepted by the verifier. So if this tuple is not in L-inc, but C and D are actually valid encodings of some code word, then the distance from this tuple to L-inc is at least D over 2, which is bigger than gamma. Then the verifier is going to reject them, and reject them with probability 1 minus S. So this is how we make sure we reject all the invalid answers A and B. You may ask, what if they have like invalid encodings for the A and B here? Then we need to use some tester for the Heidenmark code to make sure we can reject all the invalid encodings. And this tester is going to be a generalization of the linearity test of the Heidenmark code. The linearity test is known to be quantum sound, and then we improve that to make sure the new tester is also quantum sound. So in the the new answer reduced verifier is going to first sample the question XY according to the original verifier. And then it's going to sample questions or queries T0, T1, U from the PCPP verifier for the language L-inc. Then with equal probability, is going to check the proof by query T0, T1U, or check the encodings of the holding by the provers. So the key thing is that T0 is a query to the encoding of A, T1 is a query to the encoding of B, and U is a query to the encoding of pi. So here you can see the prover is not just going to compute the proof, it's also going to compute the encoding of pi. And indeed, in the honest case, the prover is going to compute A and B just like the original provers, and then compute the encodings. And then they are going to compute the proof pi to show the encoding A, encoding B are in the language LINC. And then it's going to compute the encoding of the proof and answer the queries T0, T1, and U using all these three encodings. And this makes sure they can be accepted by the PCPP verifier and the new answer reduce verifier with probability 1. And then the soundness says that if the prover is accepted with a high enough probability, then its behavior is essentially this. And I'm not going into the detail of the soundness. So this concludes the technical part. And for the summary, we show that MIP star is not robust against depolarizing noise. So noisy MIP star equals RE. Noiseless MIP star equals RE, but noisy MIP star equals next. So this computational advantage is completely destroyed. This kind of collapse of computational power is not so usual in the complexity theory, because usually you can just use fault tolerance like for BQP and stuff to make sure the noise doesn't affect the computational power that much. And for open problems, the first question is, what about general MIP star protocols? General MIP star protocols have more provers, more rounds of interactions, and longer answers. And our current techniques cannot deal with those cases. And the second question is, what state is useful for MIP star? Now we know like partial entangled states and maximum entangled states, they are all useful. But we don't know, like I mentioned and discussed in this talk, we don't know what's the effect of non-unital noise here. And the third thing is that we want to ask what properties can we certify in the noisy setting, like physical properties. One simple explanation of why noisy EPR pair is not useful for MIP star is that they cannot pass the self-test used in the MIP star protocol for RE. That's a very short answer. And then people have considered this noisy setting, and people have proved that you can certify some entangled measure on the prover set. And we think it's interesting if we can extend on that to certify more properties on in the noisy setting. And this concludes the talk, and thank you very much. Thanks.
Wonderful. That was absolutely wonderful. Very nice. We had lots of questions along the way. Hope not too many.
No, that's good. All good. Yeah.
Yeah, let's have questions. Maybe I start. So just to be sure, I mean, it means, I mean, it's extremely striking, your result, because it basically shoots down the original argument, and that for any epsilon you will not get this MIP star point, right? So that all you say is true for arbitrary epsilon.
Yeah.
Yeah. Okay. And with okay, Leonard.
Maybe the first point, because I was wondering if, like, okay, MIP star, we now have multiple number of provers and multiple rounds. Am I right in thinking that if we add multiple rounds, then basically the verifier could just run a distillation protocol with the two provers in the beginning, so that they can get their epsilon up, like they are closest to the null state arbitrarily close, which would just increase their power, right?
Wait, sorry. Can you say
like,
that again? Like in the second round, what the verifier do?
In the first round, basically the two provers perform some fidelity protocol, and they want to send that to each other in order to distill. but the verifier can just relay that message.
Okay.
So you can improve the fidelity of your bell states arbitrarily, kind of get this 1/, poly scaling that you need. And then afterwards, they have basically a good bell state, and then you can run your MIP star one, right? So if you have multiple rounds, noisy is identical to MIP star.
So the problem I see is that if the prover are not honest, if they can manipulate this fidelity relay protocol to actually send some secret message to the other, and then
yes, but this message would all be before the verifier starts its protocol, right? So the first 3 rounds would just be the verifier helping. They can communicate beforehand, so the verifier didn't give them any information. He just relays their messages, which is just their destination protocol, and then once they have sufficiently good bell state, then you run it. So I think in terms of soundness and completeness, that should be fine.
Well, I think that corresponds to like you start with high, like with the EPR pairs. Yeah, we just look at what the prover have at the point the verifier starting asking questions. So if you do some pre-processing before the start, and then at the point you have EPR pair, so then
but so my question was more multiple rounds. So right, I think if I understood your second point, basically you're considering MIP star 2, right? 2 provers, 1 round.
Yeah.
And what I think it's for me, it seems kind of straightforward to argue that if you have multiple rounds, basically 1 round can be used for distillation, and then afterwards to run your MIP star, although it should still be RE.
So you are saying like the first round is independent of the problem instance.
Just to distill the state.
Yeah, that doesn't count as 1 round, I think. Yeah,
what?
that's more considered in the pre-processing, like before the start of.
No, but like so so I think if you have multiple rounds, I guess it should be easy. The other point is if you have 3 or 4 provers, right? So they all share noisy bell states, but you have 3 provers. I think if you have multiple rounds, that you can basically recover MIP star. If you have multiple provers, do you have any ideas there?
I'm not sure how do you recover the full power.
Because you can distill in the first few rounds without sharing any information, so soundness should be tight. And then after the first few rounds, the provers have a sufficiently good bell state pairs. No, they don't. No, okay.
Yeah, maybe we can take that offline. You can send me an email.
Oh, that's an interesting point. But it's not so sure whether a sufficiently good bell pairs will do the job. It's a bit like why fault tolerance doesn't work, because it brings you arbitrarily close, but that's not close enough.
No, never mind. Okay, but no, you're considering these questions just to have an idea, or
nice.
But, to jump back on this, is it clear that if you have EPR pairs with epsilon 1 poly, that you have a working protocol? I mean, your bounds that show that MIP star breaks down.
Yeah.
Those bounds break down. Yeah, sure.
Yeah, we have this bound, but we don't have like this kind of containment if you have like 1 poly noise, that kind of things.
So it's not clear whether it will still retain the power of MIP star?
Not the full power, but you can get some advantage over classical MIP. That's my guess.
Yeah. Okay.
Yeah.
But it's not clear it's still RE, right? That's what you're saying.
I don't think it's going to be RE because basically, if you look at this one, this result here, this epsilon actually, I should mention this epsilon can be anything bigger than 0. And for anything bigger than 0, they show this content in the computable. So that means no matter how small the noise is, you cannot recover the full power.
Okay.
Yeah.
I see. Thanks.
I may have an unrelated question.
Yes, so your positivity tester, can it be of independent interest? So have you thought about other applications? Because sometimes, when you don't want to do full tomography, you just get some partial information, and then you are not sure if this matrix is positive or not. So have you thought about applications of this subroutines?
No, but But the point of giving this talk is to like inspire you guys, like getting some feedback on possible application. I think what you mentioned is very interesting. If after the talk you can send me some reference on this kind of, on when you need this kind of positivity tester, that'll be wonderful. That'll be much appreciated. Thank you.
Okay, yeah, I'll think about it. But yeah, I think it can be interesting in other contexts. Yeah, for sure.
Yeah, thank you. Thank you.
Wonderful. Are there further questions? Maybe I have one more, like on the, when you mentioned in like to think of general MIP style protocols. So what do you mean? Like protocols in a similar mindset that would overcome the previous limitations, or what is it? What does general mean in this context? I think it's what slide. How it looks like.
Yeah. So the general just means like, so general MIP style they define on like poly many provers, poly rounds, and poly length questions, and I mean those kind of protocols.
Okay.
It's kind of our bound is only limited to like constant length, 2 provers, 1 round that situation, and we are thinking whether we can generalize our technique to deal with more general situations.
Okay.
Yeah.
And what does Thomas Wittig say about this? Have you shown the result to him?
Well, he was thinking like you can generalize this to like poly-bit answers, but we thought about it afterwards. But no, the answer reduction doesn't apply directly to this noisy setting. Yeah, so. And he was suggesting maybe we can calculate some like channel capacity using the same techniques, and we are working on that. Yeah.
Okay, super. Let's have maybe a last question by Leonard.
Yeah, okay. I'll be quick. Just basically, like, I mean, this context is always relevant for Bell inequalities. With everything you describe for Bell inequalities, right? Like these non-local games, effectively on. Like which are basically just linear functionals. Like you take the data and you just basically play these linear games. Is everything you described, are those all linear functions on the level of the verifier? Like
yeah.
Okay, so it's all basically just about Bell inequalities.
Yes.
There's no subtlety anywhere, like for nothing meaningful.
There's no what?
Like it's not like the verifier needs to apply a quadratic function or be somehow like it's just about
actually, the verifier can apply arbitrary function as long as like polytime computable.
Yeah, so I'm wondering because the original result was effectively about also characterizing the quantum polytope, right? What quantum correlations are possible in some sense. So they did relate it directly to that question. And I'm just wondering whether like what you did could also just be directly related to that.
Oh, you mean like to characterize the set of quantum correlations?
Yes.
That's a good question. Good. Cool.
Like just whether there's anything else or whether it's exactly the same. Because I think for the original one it was, but here probably it might be more subtle. I don't know.
Yeah, there's some implication. Like one direct implication would be like if you want to do self-test, you can look at quantum correlations through the lens of self-test, and this result means if you want to self-test large entangled states in the noisy setting, you need a larger and larger questions. So I'm not sure if that's satisfying, but for comparison, if there's no noise and you want to self-test a large entangled state, the number of questions and number of answers doesn't necessarily grow with the dimension. So so noise causes some distinction here. Yeah.
Wonderful. That was a really great talk. I really enjoyed it. And also a good discussion, I must say. That was really very insightful. Thanks for the many contributions and questions. That was fun.